Or just that you follow the patterns, we get no reaction. But there is a reaction that takes place here. So we can figure it out using the chart method. So let's go ahead and do that. Chart method. We consult the chart. Silver is a reducing agent or oxidizing agent? It's not a very good reducing agent. It's a reducing agent. H plus is a oxidizing agent. Chloride is a sodium ion. Nitrate.
Well, the electron deficient, so that we not make it a oxidizing agent.
Yeah. Except we need something. We need nitrate needs H plus. So nitrate with H plus is an oxidizing agent. So I'm going to write this bar to connect these two. We need both of them. Water is what?
That is that is an oxidizing agent.
Oxidizing agent?
Yeah.
Yeah, the more familiar you get with this chart, less time it takes to find things, but water here. Does an oxidizing agent? No, not like that. It's a reducing agent.
So if it's going that way and it's on the right with a positive charge, then
On the right side,
it's the opposite of the direction.
yeah, it's the opposite there.
What is the difference between oxidation or an oxidationist agent?
They're opposite. That's like, what is the difference between a robber, thief, and the victim? So the robber was robbed, and so the robber was robbed. No, the robber wasn't robbed. The robber did the robbing. So that's that's what we're talking about here. The oxidizer does the oxidizing. Somebody got oxidized.
So like silver is oxidation.
I'm sorry?
Reducing agent.
Yeah, silver is a reducing agent, so it will become oxidized if that's it. Somebody's going to get oxidized by the oxidizing agent. So who gets oxidized by the oxidizing agent? Who gets robbed by the robbing agent? They're going to lose their electrons. Well, water, as you know, if you've seen this chart multiple times, there's no water occurs in two places. So water occurs both as a reducing agent and oxidizing agent. That is, if you've seen it. A lot of people don't, they don't pay much attention to that. So it's like amphoteric, but we don't call it amphoteric. All right, and then what we do? So we labeled everything. The next step is to find the strongest oxidizer. So which of those is the strongest oxidizer? Not H plus. Strongest oxidizer would be sodium's not an oxidizer. Sodium's a reducer.
Why do we have
Oh, okay. I misunderstood. Since we were talking about sodium earlier, you're talking about sodium ion?
Ion, yeah.
Yeah.
Cation.
Sodium cation is oxidizer. Correct.
Why do we have oxidizing agent and reducing agent for water? Because it's kind of neutral.
No. Neutral means unreactive. Water is reactive.
So why do we have both?
Why do we have both? Did somebody answer that? Why we have both? Right here. You see water is right here?
Yeah.
What does that make it?
That makes it a reducing agent.
Yeah. But if you've seen this chart multiple times, you would have noticed something funny about water. Water is also here, which makes it.
Oxidized.
And so what in water will oxidize? Hydrogen. If hydrogen oxidizes, it'll form hydrogen gas. Because it'll go from H plus to H. What in water will reduce? Oxide will reduce, or oxygen. So if water serves as a reducing agent, what forms? These are little patterns you pick up when you start looking at these for many, many hours. Not that anybody would necessarily, but if you want to learn something, you can pick up a lot of stuff just by looking without really having to extend yourself. So if we look at the oxidation states here as +1 -2, so oxygen's losing electrons, they're going to O2. And so water can go either way. If water is oxidized, we form oxygen. If water is reduced, we form hydrogen. Water goes either way.
There's another H2O liquid.
Yeah, we talked about that too. Does anybody remember what I said about it? Why there's two H2O liquids? There's one here and one here. Anybody remember that? Why are there two waters? And if there are two waters, which one do we pick? It's a separate reaction, but there are two waters, so which water do we pick? Water top one or water bottom one? You tell me. That's not the reason. I wonder, did anybody write it down? Because it's spent like some time talking about it. That, if the test is 90% remembering, the first step in remembering is having it written down. Otherwise, it's impossible to remember. And so this is just tips for, tips that, I don't want. You're probably tired of hearing these tips and stuff, but I had a big struggle. Okay, so the other thing available at UCLA are professional note takers. I always bought them, but unfortunately they didn't have them for all the classes. And professional note takers are very good.
How much do they cost?
A lot. They're really expensive, but totally worth it. I think for one class, this was years ago, my organic chemistry class was like it was close to $200 or something like that. It's like the price of the textbook. But boy, you have an advantage. You have a huge advantage of the people who didn't write anything down or who took poor notes. Or you had a huge disadvantage. This is why everybody buys them. They want that disadvantage. And so, hopefully you have something like that in your notes. Well, if you don't, then forget it. Why? You got to figure it out. Can you figure it out? Tell me why there are two waters. So it makes two different levels of problem. One level of problem is just remembering. The other level of problem is you have to figure it out on your own. Two levels of problem.
Is it because you take two different oxidizing agents? Then
Yeah, that's a good start. Why do we have two waters here? Because these two different oxidizing agents produce the same product. That's why. And it's not because of water being a reducing agent. It's because of these two different oxidizers. One oxidizes hydrogen peroxide. The other oxidizes oxygen. It just so happens. And therefore, when we use, which one should we use? Which water do we use? We use the stronger water. Which one's a stronger reducing agent? The one that's closer to lithium. So we picked this one. This is why I said it goes to oxygen rather than hydrogen peroxide. But I thought I didn't. I don't want to review it, so it's all right. I just went straight to that. But anyway, so we got water. Water. Why do I call it both an oxidizer or reducer? Because it occurs on both sides of the chart. This is where This is where we have two different levels of why. One level of why is this. You have to remember that as long as I give you a standard problem, you don't have to know the whys. All you have to do is follow the steps. Some people get so hung up that they can't even start a problem like this because they think they have to have some specialized knowledge. You don't have to have any specialized knowledge. All you have to do is why it occurs on both sides of the chart. That's why. It's an oxidizer, it's a reducer. That's why. That's one level. The next level, of course, we want to know why. Then you got to talk about the oxygen. The oxygen oxygen water tank is a reducing agent. The hydrogen water tank is an oxidizing. That's a different level of why, but you don't need that level of why to do this method. To do this method is very simple. You got the chart, you follow the steps. That's all you need to do. And so some people, the reason I go into this rant is because some people complain that, what am I doing? This is way too advanced. And no, it's not way too advanced. Look at what the book said. The book didn't even give you any steps. And so people complain, this is not in the book. I've been doing this method for so long, I've heard all the complaints. But it's not hard, because did I need any specialized knowledge about, why silver is a reducing agent? No, it's on the lithium side. Why H plus is an oxidizing? No, it's on the fluorine side. That's it. That's it. We don't need to know why. We just need to know, is it on the left side or is it on the right side? But you have to be careful because it depends on what chart you're looking at. Look at this chart over here in the middle. If I threw this chart on the test, then it would screw up a lot of people. Some people would be frozen because that chart doesn't look like this chart. Do you see the difference between this chart here and this chart here? It's flipped. So that just flipping that will throw people off. So I hate to say left side and right side. I like to say lithium side and fluorine side. That way, hopefully people don't get tripped up when it's not on the left side and it occurs on the right side instead. Okay, the next step is we don't need to know any chemistry. All we have to do is see which of the oxidizers is closer to what's the strongest oxidizer on the chart? Yeah. So which of the oxidizers oxidizes 8 electrons? Right side with 8 electrons. So go from fluorine. Tell me which one we hit first. Nitrate. Nitrate and H plus. Do we have nitrate? Yes. Do we have H plus? Yes. Do we have 4H plus? Yes, we do. Because this 4 is just a ratio. Does this 4 mean I need 4 gallons of H plus? Does it mean I need 4 pounds of H plus? No, all this means is whatever I have with nitrate, I need 4 times as much H plus. That's all it means. And so if I don't have enough, that's a limiting reagent problem, but it'll still react. So it doesn't matter what the ratio is. The optimum ratio is 4 to 1. I might have it, I might not. But it'll still work. I have H plus, I have nitrate. So the strongest oxidizing agent is this. The strongest reducing agent is what? The one closest to lithium. Lithium here. Oh, wait a minute. Isn't the strongest reducing agent this? It's at the bottom right. Isn't the strongest reducing agent at the bottom right?
No.
No. Yeah, different chart. Good. The strongest reducing agent is lithium. So let's just go out. See what one we hit first.
We hit sodium.
We hit sodium.
But that's an oxidizer.
We hit sodium. I don't see. Yeah, we hit sodium here. But so
That's the middle.
yeah, this is totally not the same thing. So not the same thing that maybe they should even give it a different letter. You know, but it is from the same, you know, number of protons, same nucleus. Would it be end up being water? Well, let's just keep going up the list. It could be water. Let's wait and see. Oh yeah, it's water. I see it. It's right here. You're right. It's water. So water would be the closest to lithium here. You agree?
Yeah. But it has a positive charge, doesn't
What has a positive charge?
it? Or the
Water doesn't. This
no,
one.
not the charge of water, but the charge. Power charge.
Ignore these. Ignore these right now. Is it the positive and negative? Like the positive and negative here are like temperature. If you're a positive 10 degrees C, do you move left to right? And then when you hit negative 10 degrees C, you start moving backwards because it's negative. Negative temperature means you move backwards. A positive temperature means you move forward. Is that correct? And so somebody who's positive 10 degrees C will be running at 10 miles an hour this way. Or maybe 10 miles an hour is fast. But somebody at negative 10 degrees C will be running minus 10 miles an hour the reverse way. Is that right? So when temperature flips, like we enter a different universe. So when we go from, let's say, we go from positive 10 degrees C, and then we cool it down to 0. And at 0, everything stops, 0 degrees C. And then we go to negative, and then it starts going backwards. So maybe it was like this, and then we hit 0, and then when we go negative, it starts going backwards. Is that how kinetics works? Yeah, right. And so negative 10 just means there's less kinetic energy than 0, which is less kinetic energy than positive 10. Nothing goes backwards, nothing changes. The same thing with this negative sign. This negative sign just means it's weaker than 0. What is 0? H plus. Does H plus having a 0 mean it can't oxidize anything? It's totally worthless? Is that what 0 means? No, it's what we call an arbitrary 0. So ignore those numbers because you have to have to understand those numbers, you have to have a deeper understanding, which we aren't going to get into. In Chem 1B, we've talked a lot about this. This is different than battery. Batteries, the negative does mean something. In batteries, a positive means electrons go left to right. A negative means the electrons going backwards in the circuit. And so batteries is slightly different. But anyway, can I use this?
No.
I can't use this. Why?
Because it's combined with
Yeah, I'm missing this. I need SO2. Do I have any SO2?
no.
No, so I can't use that. It'd be silver, right? Silver would be the. So my oxidizing agent is nitrate. Okay, what I'll do is I just copy down the reactions here. So nitrate plus 4H plus 3 electrons. Just copying it down off the chart there. Yields NO gas plus 2H2O. 2H2O liquids. And then silver, we'll just copy it down, but silver I have to reverse. And so what I'm going to do is I'm going to take silver, which is now the reactant, and have these as a product. Because I don't have silver ion, I have silver metal. So silver metal is going to go to silver ion, plus an electron. And so here's my oxidizing agent. Here's my reducing agent. Now at this step, let me show you. We want to do the conjugate relationship at this step because that makes life easier. If you do this at what we call the half reactions, it's a lot easier because if this is the oxidizing agent, the 4, do you know what this is? This is the reducing agent in the reverse. So the oxidizing agent and the reducing agent, this is the conjugate pairs. If this is the reducing agent, then that means silver ion will be the oxidizing agent going backwards. This helps us in determining driving force. Okay, what's the next step? Step 4, combine these, making sure that the electrons are balanced. The balanced electrons, I got 3 electrons here in the top, I have 1 electron, so I'm going to multiply the bottom by 3. And then add these. So when I add these together, I'm going to get 1 nitrate plus 4H plus 3 silvers. Now the 3 electrons have to cancel, so these 3 electrons will cancel these 3 electrons because they'll do 3 times 3. So those are like spectators, but they actually participate.
Wait, so the electrons cancel? Why
Yeah.
wouldn't they add the 6?
Well, I'm going to do it. They don't add because we have electrons on the left side and electrons
Oh,
on the
those
right
on the
side.
right, got it.
This is the NO gas, it's 2H2O liquid, plus 3 silver ions. Okay, now we determine the driving force. To determine the driving force, we have everything laid out here. The nitrate and the H plus is our oxidizing agent. The silver is our reducing agent. The NO plus water, that's our reducing agent. And the silver ions, that's our oxidizing agent. So we compare the oxidizing agents on the left side and the right side and see which one is stronger. Silver ion here versus nitrate and H plus. Which one's stronger? Nitrate and H plus. So we're going from a stronger oxidizer to weaker oxidizer. And the reducers are the same. Silver metal is a better reducer than NO and H2Os. So this is stronger reducer to weaker. And then we simplify. Well, we can't really simplify anymore. This is as simple as it gets. This is called the net ionic equation reaction. And so we have driving force. And so the reaction is the silver metal will be attacked by nitric acid in this. All the other stuff should be spectators.
If you had a stronger oxidizing agent that goes to a weaker oxidizing agent, but then a weaker reducing agent that goes to a stronger reducing agent, would there be driving force?
It never happened. That means you made a mistake. It's because of the conjugate relationship.
Right.
It's impossible that that happens. Well, let's see how long this video is. Maybe we'll do this. Dissolving. Who would want to dissolve silver coins?
It's going to be a couple of short videos. This one is going to be on dissolving silver coins. I've got 140 grams of coins out there. We're going to dissolve them into a silver nitrate solution.
Okay. So who's using nitric acid? Let's just zoom in. Look at the, he has mini hoods. It's pretty cool.
And that second jar.
Should move that other jar. First one looks like copper.
Step back a bit now. You can see the reaction's instant. And the input is working perfectly.
The brown gas is generated as nitrogen dioxide. There's going to be some copper in the middle of the quarter. But either way, it is all both. That's it's a home lattice.
What would you do with the product of that?
Silver nitrate?
Yeah.
What would you do?
But that's the product isn't silver nitrate, it's nitroxide gas and water and then silver ions.
Yeah, well, if you have 4 H pluses, then you have 4 nitrates. 3 of the nitrates didn't react. Where did the 3 nitrates that didn't react go? Well, they need to be here. Nitrates need to be here to form the silver nitrate because we can't form cations without having anions present. So that's why the three nitrates respectively. We went straight to the net ionic equation here. The NO gas we got to get rid of. What happens with the NO gas is this. NO gas is a clear colorless gas. It's a CCG, but it's oxidized in air, and then it forms NO2 gas. The NO2 gas is the brown gas here. It's the smog. So this is called nitrogen monoxide or nitric oxide. This one's nitrogen dioxide. Nitrogen dioxide is brown. And so there's one more redox reaction that occurs in this. What do you do with that? Well, get rid of it safely. It's the best. You know, but some people will react it with water. When they react it with water, it undergoes a Lewis acid-base reaction. Remember what happened to CO2 in water? When CO2 mixed with water, it was a Lewis acid-base reaction that formed carbonic acid. So NO2 can be reacted with water as well to form nitric acid.
Is it just because you're so familiar with this that you can tell right off the bat if something's a Lewis acid base or if it's Bronsted-Lowry? And how do you tell that just by looking at the reaction?
No, how I determined it was because, do you remember the CO2 in water?
Yes.
If you remember the CO2 in water, you go, well, CO2 is a gas, NO2 is a gas, maybe they have a similar type of reaction. What caused the CO2? I'm just doing it by making a pattern association. And so, what made CO2 an acid? Does anybody remember what made CO2 an acid? It's a delta plus on the carbon that made the CO2 the acid, and so it was susceptible to attack. And so I'm just doing kind of the similar, although NO2 has a totally different structure, you know, in certain ways it's similar. In certain ways it's similar in that, you know, there's going to be a plus charge here, there's a minus charge here, but you know, nitrogen could be susceptible to attack by another pair of electrons here. And we could have something similar. In fact, this pattern holds. In chapter 19 you learned this, so I'll just I'll just tell you. The pattern is this, and we can boil it down into a very simple pattern. This is not a law, but the pattern is non-metal oxides are Lewis acids. So non-metal oxide plus water yields an answer. Metal oxides are Lewis bases. So I gave you 2 homework. I posted some homework. And last night I was thinking, should I assign this? I thought I better assign this because we did CO2 and water. Since we did CO2 and water, I thought it was fair to assign. But you're going to have to make a couple of predictions about what you expect to see. Those are just based on familiarity. And how you get familiar, is this. You work in the field for 30 years, but you don't have 30 years to work in the field. So what you do is you cram 30 years of experience into one. How do you cram it? Well, you look at it. If you read through every day, then that's like cramming 30 years. You go through it every day. That's what I did as a student. I wanted to get 30 years of experience rapidly. Then I'd look at it every day, because if you look at it once a month or something like that, you aren't going to get it. And so that's how you build the familiarity, and that's how you make the connections, because it's all about making connections. How you make the connections, I studied about this because I was very interested in it. And what I learned was that, you get it in your subconscious. Once you get it in your subconscious, your brain is always working. Your brain is working to make neural connections and trying to interconnect all these concepts. But how long does that take? You only have 10 weeks during the quarter. In order to make those neural connections so that you can answer the advanced problems on the test, you got to make those neural connections quickly. And so this was my whole goal. This is why I was doing that, reviewing on a daily basis, so that I didn't have this thing happen. I told you what happened at Ralph's. Did I tell you guys what happened at Ralph's? There was a challenge problem, and I was so close to getting it. I felt, oh man, I just about there. And then we ran out of time. It's a 3-hour final exam. About 30 minutes later, I was at Ralph's getting some snacks, and then I was waiting in the line. Boom, it hits me. Just out of nowhere, just hits me. I got the answer. Oh, so simple. So simple, but I couldn't answer it within that time, and then that really frustrated me. And that got me thinking, about this. And so how do I make that connection? Because I've seen it. Now, obviously, you probably haven't seen it, or this, but the more you can, the better you'll be. And I don't expect you to know everything, it's too much, but, but I do expect you to know more than what because right now, because I've taught many different levels of classes. I've taught upper division classes, graduate level classes, lower division, and I've taught lots of lower division Chem. And I'll tell you, man, when I'm teaching at UCSB, the students are on top of it, and you gotta expect there's going to be a big shift, when you transfer, a big shift in competitiveness, because I get a feeling for what and so it's which is fine. This is just the beginning, but you got to think, if you're planning to transfer to UC, you gotta kick it up, kick it up a notch, and then you'll be okay. Just make sure you're on top of it. It. I've seen a lot of people. What the dropout rate for transfers is huge. It's surprisingly big. The dropout, but it's not as big as the dropout rate for incoming freshmen. The dropout rate for incoming freshmen is horrendous. When they told me the percentage, I was shocked, because I thought, the people who got into UC straight from high school had it all together. It was huge attrition. The percentage was a surprisingly big number. You'd never think of it being, it was like 40%. That's what it is.
And what is it for transfers?
Transfers was still high. It was like 20 or 30, but still lower than incoming freshmen. The dropout rate, it's still a lot, and I know a lot of those, because I was a student with a lot of dropouts as well. It's not to say, okay, you're labeled as, a dropout and unsuccessful. They went on to do, great things, They just didn't finish, that's all. The people drop out for different reasons, One guy I know, actually I know a bunch of dropouts. But, they're probably a lot happier. Dropped out, sticking with it. But anyway, so that repetition is key. Otherwise it's too hard to come up. It's so hard to come up with the connections and the answers without that.